Hello everyone, today I'm going to give you a survey of the texture synthesis. My introduction will be divided into six parts. First, I will going to tell you what is the texture synthesis, and then I will introduce two main kind of methods, that is the non-parametric methods and the parametric methods. And then I will introduce two kinds of non-parametric methods, that is the pixel-based methods and the patch-based methods. And then I will introduce the parametric methods. The time is limited, so I will only introduce the convolutional neural network-based method here. And then finally, I will introduce my opinion of the future work. So first, what is the texture synthesis? The texture synthesis is a process of generating a new texture image from a sample or a small portion of an existing texture image. The goal of the texture synthesis is to produce a new image that has the same visual appearance and the statistical properties as the original texture, but is different in some aspects such as size, orientation, or color. And there are two main kinds of methods to solve this problem. The first kind of method is the non-parametric method, and this kind of method uses a small portion of an existing texture image as a reference or sample to synthesize a new texture, and they do not make any assumptions about the underlying statistical properties of the texture and rely on local pattern matching and blending the techniques to construct the new texture. And as for the parametric method, this kind of method make assumptions about the statistical properties of the texture and use a mathematical model to represent it. They typically require more prior knowledge about the texture and its parameters, such as size, orientation, and color distribution. First, I will introduce the pixel-based method, and as we can know from its name that this kind of methods synthesize the output texture pixel by pixel. In 1999, Afros and Lang proposed an algorithm using the nearest neighborhood search algorithm in order to generate a texture by directly sampling new values from the input sample. We can see from the left, the key idea of this method is to search for pixels whose neighborhood's visual distance is smaller than the threshold we assign in the input texture. And we randomly sample in the pixels we pick and assign the value to the pixel in the output texture to be synthesized, marked as the red one on the left. In this method, however, only the pixel which have already been synthesized can be considered as the valid neighborhood. So this introduces the problem of the varying neighborhood, which may improve the computational cost. To solve this problem, in 2000, Wei and Loy optimized the former algorithm by introducing a fixed neighborhood and a fixed synthesizing order, such as the raster scan ordering. Also, this method introduced the multi-scale synthesis and the tree-structured vector quantization, known as TSVQ, to speed up the whole algorithm. And the key idea of the multi-scale synthesis is to represent large-scale features by a relatively small number of pixels. The key idea of TSVQ is to build a tree-like structure data, and we use the tree to search until we read the leaf node. And the path that we go through is the neighborhood that we want. And in 2001, Ashkeman proposed an algorithm which first we explore the idea of coherence, which improve both the quality and the speed of the synthesis. And these two are better than the algorithm that we discussed above. The key idea is to use the relative position of the neighborhood pixels and the center pixel. We can see the picture on the left. If the neighborhood pixel is one pixel to the left and one pixel above with respect to the center pixel, then if the neighborhood pixel is synthesized, the candidate of the center pixel in the output image is one pixel to the right and one pixel below to the matching pixel of the neighborhood in the input texture. And in 2002, the Tom proposed an algorithm based on the k-coherence, which improved the speed further. And the idea of the k-coherence is an expansion of the idea of the coherence. First, we use the coherence to build the original candidate set, and then we expand the candidate set by expanding each single element of the candidate set to the set whose size of k, where the k-1 pixels are the most similar k-1 pixels of the single pixel in the original candidate set in the input texture. And then I will introduce the patch-based method to you. This kind of method, we can also know from its name that it synthesizes output text by patch. And that introduced the problem of the conflicted regions. and this also introduced the problem of the high computational cost. First, in 2000, the Prom proposed an algorithm to solve this by simply overwriting the old patches with the new ones. And in 2001, the Liang proposed an algorithm to solve this by blending overlapping regions. The idea of the Liang's algorithm is similar to that of the pixel method of the Afro-Lang. The difference here is now we need to search for the region instead of a single pixel, and the condition that decide the similarity of the region is the boundary. However, these two methods may introduce the artifact, that is, the unnatural visual effect of the output texture. And to solve this problem, in 2001, the Afros and Freeman solved the region blending problem by using the dynamic programming to find an optimal path to cut through the overlapped regions. The basic idea of the dynamic programming is to solve the problem such as recursively. For example, we have a sequence of the number, and we need to give the largest number of the sequence. Now we have the largest number of the n-1 element and the nth element of the sequence. And we only need to compare of the between these two elements, and then we can tell the largest number of the nth element. And that is basic idea of the dynamic programming. And in 2003, the Quadra improved the former method by using the graph cut. As for the detail of the graph cut, you can refer to the text of the graph cut. I will not discuss it in detail here. And in 2000, the Xu proposed a method which formed a new texture on the base of the algorithm of chaos mosaics. I think this algorithm is interesting, so I will introduce it briefly here. The key idea of the chaos mosaics is to obtain the new coordinate of the patch recursively, and we paste the patch to a new coordinate and to form a random visual effect. And finally, I will introduce the convolutional neural network-based method. In 2015, the GE used the convolutional neural network VGG19 to derive the feature space to construct a model of the natural textures, and the loss function is computed by the Gram matrix. In 2016, Ulyanov used the forward network to solve the problem of the computationality in the former problem. The loss function is still computed using the Gram matrix. In 2017, Ulyanov optimized the network proposed by introducing the instance normalization and introduced a new formulation that learns generator that uniformly sample the Jewish ensemble. In 2021, the Hayes introduced the sliced Wasserstein loss as the loss function of the convolutional neural network to solve the problem of the G algorithm, which loses some high-level statistics. The structure of the network is still VGG19. And here is my guess. I think we can try to combine the network proposed by the Ulyanov in 2016 and the loss function the Hayes proposed in 2021, and we can see what is going to happen. And that is all for today. Thank you for watching.